Good evening. Now we have next video that is again continue that is related with your clauses of IS 456 plain and reinforced concrete code of practice. Now we have seen we have mainly with two limit state. One is limit state of collapse, which is flexure, and limit state of serviceability. Here we will see limit state of collapse. Now assumptions that is designed for limit state of collapse in flexure based on are as follows. So now first plane section normal to the axis remain plane after bending. What does it mean? Suppose we have any circular section. So we can take our refill. So we have refill is in this fashion circular. And now if I will bend it, what will happen? So we have in this fashion. So now before bending, if we will see our section of this refill is circular. And after bending, we do not have this circular, actually it will be little bit, we can say deviated from your circular section. But this assumption shows sections normal to the axis remains plane after bending. So normal to the axis. So we have this will be our axis normal to it. So same way we have this will be now axis. So normal to it, we can have circular section. Second, that is the maximum strain in concrete at the outermost compression fiber is taken at 0.0035 in bending. Now this is stress strain curve. Keep in mind, students do not remember at the time of oral where we have stress and where we have strain. Stress we have that is on y-axis, unit is Newton per mm square, and strain is on x-axis, which is unitless. Now we are with three curves. So for this second, we have this value 0.0035. Now we will go to the next. So you can see the relation between the compressive stress distribution in concrete and the strain may be assumed to be rectangular, trapezoidal, or parabola, or any other shape in which results in prediction of strength agreement with the results of test. We have different curves, that is rectangle, trapezoid, parabola, or we have combination. Now an acceptable, you can see an acceptable stress strain curve is given in figure 21. So we have this as figure 21. For design purposes, the compressive strength of concrete in the structure shall be assumed 0.67 times the characteristic strength. So here we are going to assume to reduce this to 0.67, and that is nothing but your, we can say, size factor. Because for cube, we have dimension as 150 by 150 by 150, and we can maintain the quality. But when it will go to the sizes of the elements, then it becomes difficult to maintain same quality, and therefore we are going to reduce that value to 0.67 FCK. And then we are going to apply partial safety factor, and we know always for materials, partial safety factor we have to divide, and for loads, we have to multiply loads by factor of safety. So that is most important. Keep in mind, for strength, we have to divide. For strength, divide by partial safety factor, and for loads, multiply by partial safety factor. Now you can see that value is given. The partial safety factor gamma m is 1.5. So if we will divide it, then we will get this value as 0.446 FCK. Gamma m is given 1.5 over. And then if we will go to this, that is area of stress block. Now we are going to consider only this value. Now I will not go in detail. You know already with all this. So we have to consider total area, and that total area gives us compressive force, and that compressive force is unit Newton per millimeter. So you can see area of stress block, that is compressive force, but unit is Newton per millimeter, definitely asked in orals. And this is 0.42 XU, which is in millimeter. In next, we have plotted this. So if you multiply it by B, so we can have 0.36 FCK XU into B. Now this becomes your force, compressive force. And unit is newtons. Now where it will act, given on page number 69 that we will see later. Now we are going to neglect tensile strength of concrete. So if you remember, when we will go for any neutral axis, so we are going to consider concrete above this. Means if we will draw shear stress diagram, stress diagram, then we are in this fashion. And we have this will be compressive force. We are neglecting the concrete which is below neutral axis where we have tension. So concrete is considered which is in compression, and therefore tensile strength of concrete is ignored. Means we are going to neglect the concrete which is available in tension zone. Then we have the stresses in the reinforcement are derived from the representative stress strain curve for the type of steel. Typical curves are given. So now you can see. So that we will see that also we are in the next slide. Now the maximum strain in the tension reinforcement in this section at failure shall not be less than. So we have this value Fy upon 1.15 ES plus 0.002. Means if I will draw this strain diagram, so we have strain diagram in this fashion. And then we have this value that is at level of steel is 0.002 plus we can write Fy upon 1.15 ES. This is our strain diagram. So keep in mind this is steel. And here also we have strain for concrete. We have this value 0.002 and we have this value 0.0035. This is strain diagram. This value we have, if you calculate this, then we have this value as 4/7. And we have this value as 3/7. And then if we will draw this stress diagram, then we have stress diagram. You may ask draw stress and strain diagram. So we have neutral axis over here and we are being in this fashion. And then this will be TU and here we have CU. CU is always in rectangular portion because if you calculate this value, we have this value that is 0.416. We have this value 0.416 XU. So that is in rectangular block. So CU and TU. And then we know we have this value which is lever arm, which is D minus 0.416. We will assume 0.42 XU. Do not say it is in parabola because 3/7 if we will calculate, then we have 0.4, then 2 remained, and then we have 4, 2, then 6, 4, 2, 8. So we have 3/7 XU is 0.428, and we have CU at 0.416. So 416 will be in rectangular because depth of rectangle we have 0.428 XU. then this will be actually shown over here. So we have this value. If we will see this value, then we have this as actual, we have 0.416. And a rectangular portion, if we will see just below, so we have this will be 0.428. That is most important. Keep in mind, this is 0.36 FCKXU. Unit will be asked in the orals. So unit is Newton per millimeter. How? FCK is Newton per mm square. XU we have millimeter. 1 millimeter gets cancelled. And we have Newton per millimeter. How will be force? Multiply this by B. So 0.36 FCKXU into B. That will gives you CU, compressive force, which will act over here. And then we have at this we have TU. So that is most important one. Then we have page number 70. Just I mentioned this. So we have strain again on x-axis, stress on y-axis. So here we have definite yield point, and therefore we can directly write Fy upon 1.15, and that will be our stress for mild steel 0.87 Fy, and that will be I think 217.5. Just I will check it. So we have 0.87 into 250. So yes, 217.5. And this is constant because we have this as definite yield point in case of mild steel. But if we will go to tar steel, that is cold deformed bars, then we have in this fashion. Now we have this will be 0.002. This we are generally considering as 0.002 proof stress. Now, what are these values? So all these values given, these are inelastic strains. Inelastic strain. Then how we will get total strain? I already told in the class. Total strain we have. Total strain equal to elastic strain plus plastic strain. Elastic strain plus plastic strain. From where we will get elastic strain? So we have epsilon elastic, that is equal to stress upon ES. Now from where we will get stress? So we have now first value we have 0, and for this value we have 0.85 Fy. You can see over here. Then we have this elastic 0.8 Fy 415, and ES we have 2 into 10 raised to 5. This is elastic. And then what will be total? So as here we do not have any inelastic, so it becomes 0. If I have to find at 0.85 Fy, then for 0.85 Fy, we have total strain equal to 0.85 into 415 upon 2 into 10 raised to 5, plus we have value for this is 0.0001. You can see for this 0.0001 first dotted line, we have this value as 0.85 Fy. Now if we will go 0.9 Fy, next value we have 0.0003, we have this value. For next we have 0.0007, that is 495. For 0.975, we have 0.001. And then for Fy, we have this value 0.008. So yield stress is considered at 0.002 proof strain, and we have considered value over here, that is Fy. And we have to divide actually it by gamma m. So 0.8 here actually we have into gamma m. So we have to multiply below 1.15, we have to consider. Here also we have to consider 1.15. And then we are going to get, or you can write it as 0.85 into 0.87, one and the same. And likewise, we have to find total strain. In orals, you should be in position to find the total strain. And now these limits, we know we have already seen this. So how we will find this, that also we know. So we have this. So if I will draw this, then we have this as 0.0035. We have this value as XU. We have this value D minus XU. Here we have 0.002 plus 0.87 Fy upon ES. And then we are going to be with XU upon D minus XU, and that is equal to 0.0035. Should be in position to answer like this: 0.002 plus 0.87 Fy upon ES. Now, if we will take ES up, then we have XU upon D minus XU. We have equal to 0.0035 into ES divided by 0.002 into ES plus 0.87 Fy. And componendo and dividendo, if you will do, then you have XU upon D, which is known as KU, and that is equal to 0.0035 into 2 into 10 raised to 5 divided by 0.0035 plus 2, then we have 0.0055 into 2 into 10 raised to 5. We have added this, means 0.002 ES plus 0.0035 ES, and then we will get 0.0055 into ES plus 0.87 Fy, and from this we will get KU is equal to 700 upon 1100 plus 0.87 Fy. So if we will put Fy 250, you will get value 0.53. If we will put Fy 415.48, Fy 500, 0.46. So this, you should be in position to solve this. So now we will stop here only. Remaining part we will see in the next video. Thank you.